rational exponents. Rational, the root word is ratio. Ratio in math means fractions. And that's because radicals have their limits. There's only so much that we can do with radicals until we can figure out a way to write them as a fraction power. Because if we do that, all the rules that we know for exponents that you guys absolutely know from your test results are going to help us, because we can use all of those rules as we go through and work with radicals. So we're going to simplify expressions with, there we go, rational exponents today. And we're just going to get the basics today. We're not going to do anything incredibly difficult. First off, because we've got guys out there taking a test and a lot of people absent today, but we just want baby steps and get used to the idea that radicals can be written as fraction exponents to allow us to do all the math that we need to do. So if we have a to the something, and we need that to represent the fourth root of a to the third, then knowing what we do, we know that a to the x times a to the x times a to the x times a to the x would have to give us a to the third. Now why do we know this? Because of the slots. Uh-oh, that's not aligned. Wow. Alright, so there's our slots. And just like we were doing before when we talked about radicals, we know what we want to happen here is we need something in those four slots that would give us a to the third, because this was a fourth root. That's what we're looking for. So we have to think, well, how's that going to happen? Well, these are all the same base. And our rules for exponents tell us that we can go ahead and add those exponents. So that would tell us that a to the 4x has to equal a to the third. And if the base is the same, 4x is going to have to equal 3. It has to. That's the only way this is going to work. And if we solve that for x, we're going to divide by 4 and see, okay, we're going to be able to represent the fourth root of a to the third as a to the 3/4. That's what we have to do. So you've got blanks down there, but I didn't want to have to scroll back up to show you everything. So like it says, we'd add those exponents and get a to the 4x equals a to the third. We'd realize the bases are already the same. That's not what we have to get equal here. We have to get the 4x to equal 3. And that would give us x equals 3/4. So that tells us that the fourth root of a to the third is really the same thing as a to the 3/4. The good news is this works in general too. So if we hadn't had a 3 and a 4 there, if we put b's and c's in there, this will always happen. So how it works is we always end up with our little fraction with the power on the top, the exponent, and then the index is in the denominator. It's always going to end up happening. So we can take any radicals and we can change them in fraction powers and then use all of those rules that we know for exponents. So like it says down here, you can write a radical expression in equivalent form using a fractional, a rational exponent instead of a radical sign. It just takes some getting used to. First of all, fractions are not our favorite thing in the world. Generally, they're on the list a little higher than decimals. Most people can't stand working with decimals by hand. But with fractions, we can represent the situation and think, okay, now how do you work with fractions? If you want to add or subtract fractions, you have to have a common denominator. But if you want to multiply fractions, you just do top times top, bottom times bottom. But we follow all the rules we already know for powers. So like it says, we're going to use a rational exponent instead of a radical sign. In general, the nth root of x equals x to the 1 over n. Now, where'd the 1 come from? Where did it come from? Remember I told you before, power is going to go on the top, and exponent, or the index is going to go on the bottom. Go.
Was 1 already the power?
It is. That's a little x to the first. So that power of x to the first goes on the top, and then that index goes on the bottom. And then it says, like the radical form, the exponent form indicates the principal root. What does that mean to us? That means when the root symbol is already there, that means they just want the positive one. They don't want us doing plus or minus. Especially as we just start off with that, we don't need that extra little piece. So if we have 36 and it's the square root of 36, we're supposed to tell ourselves, okay, wait a minute, this is 36 to the first, and that's a little imaginary 2 out there. So exponent goes here and index goes down here. 36 to the 1/2 is the same thing as the square root of 36. Cubed root of 64, again, it's 64 to the first, so that'll be 64 to the 1/3. Fourth root of 16, 16 to the 1/4. So the exponent, really the power of the number, and then we have the index on the bottom. So we're going to jump right in and do some simplifying expressions with rational exponents. And here they have us working backwards right away. Because again, whenever we do forwards in math, we have to be able to do backwards. So they've got 2/16 to the 1/3, which at first doesn't make a lot of sense to us until we realize, hey, this 3 was supposed to be an index. So it's like we're translating. You know, we've got this alien language right now of exponents with fraction powers, and we're going to change that into what we know about radicals. Is there a number that would give us the cubed root of 2/16 nicely? 6. Give us a 6. In B, we have 7 to the 1/2 times 7 to the 1/2. Well, we're supposed to notice, hey, these 7s are the same. These are bases. This is one of our properties of exponents here. We know that when the base is the same, we keep the base. And if we're multiplying, what are we supposed to do with the exponents? Add them. 1/2 plus 1/2. Well, that's 2 halves. That's 1. That's 7. This is another one of those days, everybody. I want you to look up here. I love how we can write secret code in math without a lot of difficulty. You know, you write something like this and you realize, hey, that's just 7. It's a way to manipulate the numbers and get them to do what you want them to do. And that's our job, get things to look the way that we need them to look. So now, looking at C, and C is a little different. Because the bases aren't the same, but the powers are. Hey, we've done that before too. We've said, you know what, when that happens, keep the power, but go ahead and do the math. So 5 times 125. So 5 times 1 is 625. And now is when we have to translate in our noggin and say, okay, wait a minute. 1/4 power, what's that the same as? 4th root. And is the 4th root of 625 something we're supposed to know? It's 5. It's 5. So translating in and out of that rational exponent language and radicals of all things, back and forth between those two pieces. So we've got an A, B, and C down here. Give those a try, please. And you know what? When you're done with them, chicken wing and elbow partner. Check in with somebody and see if you're getting the same thing. They are. Do that translation. Well, I didn't see which you are. Well, either everybody's wrong or everybody's right. Because everybody has 8, 11, and 6. Everybody's right. Because we've got the square root of 64, which is 8. We've got 11 to the 1/2 plus 1/2, which is just 11 to the first. And then we have 3 times 12 to the 1/2 power, which is 36. And then the 1/2 power is the square root. And away we go. Now I realize you probably didn't write down all of these steps. And that's fine. You know, just know that when things get a little more complicated, you might want to see some little steps in your notes as you go through. Because right now, notice our numerators are 1s. That's not always going to be the case. We're going to have some things where it gets a little bit tougher. So down here it says if the nth root of x is x to the 1 over n, it follows from the law of exponents that for any real number, here's where it gets tougher, the nth root of x to the m, just remember, the index is always the denominator. The index is always the denominator. So your power's going on top, your index is going on the bottom. So when we look at this and think, well, my power is m, that's going to go on the top. Because m times 1 over n with fractions would be to the m over n power. And like it shows, first forwards and backwards. You know, we can change it into a fraction exponent and then put it back in a radical if we need to, forwards and backwards. So our definition of a rational exponent is just basically this. I mean, that's what we need to be able to do. So our key concept here is using those rational exponents. Remember that your power is your numerator and your index is your denominator. And they did this with color. And so one of the things I'd really like you to do is grab one of those highlighters out of your bag, and the key here is going to be keeping track of that denominator. So I want you to go through and highlight all of those little n's. So you can see there's only 2 places those n's are going to show up. That's going to be either the index or the denominator. Thanks, Sam. Index or the denominator. Now the reason I'm just having you highlight that one and not both, you'll notice there really are 2 different places that m can go. M could be under the radical symbol or it could be outside. It doesn't matter. So that one, wherever you put it, is going to be just fine. But our index always has to be the denominator, no matter what. And like it says, if m is negative, a can't be 0. We can't have our base be 0 as we go through these things. So down here we have, what are x to the 3/7 and y to the negative 3.5 in radical form? Oh, goodness. All right, well, let's see here. I know the bottom number was the index. So x to the 3/7 has to be the 7th root of something. And now, like I said, we're just going to use the 3 as a power. It doesn't matter if we use it here, or if somebody decides, you know what, I'm going to do this. I'm going to do the 7th root of x, and then I'll just cube the whole thing. Because sometimes it's easier to do one than the other. And that would be if x is a very large number, you might not want to cube it first before you take the 7th root. If this is a really large number, we probably want to take the 7th root and then cube it. So again, the numerator, we get to decide, depending on what we see in the problem. Do we want to do the cubing here, or do we want to wait and do the cubing here? So now with the y, they're trying to mess with our heads a little bit. They did not write negative 3.5 as a fraction. What's negative 3.5 as a fraction? Negative 7/2. So you need to think of it as negative 3.5. And then, just like back in elementary school, you multiply these 2 and add the numerator. So negative 7/2. So they're trying to make this a little bit harder for us here. So why the negative 7/2? Let's see. Oh, it's got a negative exponent. What does that mean? Y can't equal 0. We're not going to raise it to a negative exponent because it would be 0 where? In 2 long since you took this. What do negative powers do? Reciprocals. Flip it. Right now it's in the top. It has to move to the bottom. Absolutely has to. And now we look at it and say, well, for absolute certain, we're talking square root, because this is a 2. Now I could put the little 7 here, or here, depending on what I see when they put numbers in there. It would be easier to raise it to the 7th power first and then take the square root, or would it be easier to take the square root and then raise it to the 7th power? But both of those answers are perfectly fine. So now there's a got it for you. So again, while you're at your desk, go ahead and do these backwards. So you have the radicals. You're going to write these with fraction powers. Which one goes to the bottom of the fraction? Square root of 8 to the 5th. Saw that on everybody's paper, but not everybody had the same answer. Which one goes on the bottom, the power or the index? Index. So the 3 is the power. 5 is on the bottom. That needs to be 3/5. So we have to know, hey, index, denominator. All right. Now I'm going to go to some, well, I want to call it trick problem, but they're trying to make us make a mistake. It says, what are the expressions W to negative 5/8? What do you see first? Which one of those should be your index? 8. That's up to you where that power should go. Well, if you want the 5 right under the radical, you could certainly do that. You could use parentheses and put, in fact, I'll write it both ways. Because it's a matter of which one works for the numbers that they are giving you. All right, how about W to the 0.2? What do you have to do first? Make it a fraction. 0.2. Shouldn't really read it off like that, should I? 2/10. What does it reduce to? 1/5. So what does that mean? What you put for the next step? 5th through the W. It's the index. The 5 is the index. So no power to our W in this one because it's a 1 up there. Let's see. Well, it's pretty obvious you don't need to move to that one. So why don't you go ahead and do B. I am Sam and Eli are recording. And I'm certain you were done with it, so I wasn't even going to try and get down the aisles here. This one I know you're going to do well at. So, oh, it's X and Y. Here I am writing. X to the what? 3/4. And then Y to the 4/5. There it is. Index, denominator. That's what we have to remember. So C says, refer to the definition of rational exponent. Explain the need for the restriction that A can't be 0 if M is negative. Well, let's find one of our negatives here. What would be wrong with making W 0? There you go. I mean, that whenever we have division, that's exactly the problem. The problem is, if there's division, we cannot divide by 0. Don't like to say we can't do stuff in there. Don't like to say that, but can't divide by 0. So, problem 3 is a word problem already. And this must be one of those really hard ones. It's a formula problem. That's all it is. It's got a lot of blah, 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 but it's a formula problem. Planetary motion. Kepler's third law of orbital motion. This is, in fact, when you get to pre-calculus, we derived this formula. Kepler's third law of orbital motion shows how you can approximate the period P in Earth years it takes a planet to complete one orbit of the sun. There's something to think about. Years on the other planets are not the same as Earth's year. Those that are farther away from us, it's going to take them longer to get around the sun. So what we want to do is think of it mathematically in terms of Earth. I mean, everything that we do here on Earth, we want to know in terms of Earth years, Earth hours, Earth minutes. And so what we do is we try to figure out, okay, if you're on this planet, what would it be like if that planet were Earth? That's what we're doing with this formula. So it says use the function P equals D to the 3/2, where D is the distance from the planet to the sun, in what are called astronomical units. That's a capital A and a capital U. Look at this number. About 93 million miles, or the distance from the Earth to the sun. How many Earth years does it take Mars to orbit the sun? Okay, so I look at the picture, and I realize it said D is the distance from the planet to the sun, and that's supposed to be in AUs. Well, there it is right there, 1.52 AUs. So this is just a calculator problem. P equals 1.52 to the 3/2. Calculator will do that. We put it in right. We don't need to change this into a radical. Oh. Get my TV turned on. Oh, in case you didn't read the little message up there, I'm lucky enough to have hall duty and bus duty now until March. So in the morning it might take me a little longer to get stuff ready for us to go. So let's see, we need 1.52 to the, and again, always use parentheses with your fractions. The calculator will love you for it. 3/2. There it is. Calculator doesn't need this to be a radical. So about 1.87 years. So almost 2 Earth years for Mars to orbit the sun. So the seasons are a little longer on Mars, but so are all the temperatures and everything else. So yeah, this will be real tough for you here. We want to do A, Venus, and B, Jovian. I don't know why it's called that, Jupiter. That must not be a good way to say. Yeah, it would be bad, wouldn't it? There really isn't a way to say Jupiter. So go ahead with your calculators, and we'll round it 2 decimal places here because that seems to be what they're doing. So let's see. Venus and Jupiter. So really with these 2 problems, what I'm trying to do is make sure that everybody realizes if you use parentheses for your fractions, the calculator will be able to give you exactly what you need. And everybody punch these fractions out in. Oh, let's see, 0.61 for Venus. So 0.61, 61/100ths of a year for Venus. And then 12.76 years for Jupiter. Our objective, simplify expressions with rational exponents. 43210 means how you feel about our work with rational exponents today. Some of you it's like fractions, oh no, but it's okay, it's okay. We'll deal with it as we go. But that's as far as I wanted to get today, was just a little baby steps into it. And we'll start on a little more complicated simplifying tomorrow. So away you go.